It's your first day of organic chemistry lab. You're doing liquid extraction. It's your first time that you have no clue what's going on, and the first time that you get a 216% yield. So, what went wrong? And how does that lab technique actually work? And more importantly, what you care about, how are they tested on the MCAT? Okay,
One
let me
time I got
finish
an
it out.
896% yield and I submitted it.
If you're in this program, CP6, high yield, what are we covering? There was so much high yield material in this. It was insane. It's chromatography and separation techniques, which is what we're covering today, but it also had like nucleic acids, amino acids, protein structure, and even intermolecular forces, which was more of a mid yield thing. But I am not going to go over all of those in the same
She
video.
does not remember
that video. I don't remember a single bit of it unless I prep it for these videos.
I'm reading
I'm
off a
just kidding.
teleprompter.
But anyway, today we're going to cover chromatography and separation because we've covered all the other things in previous videos. And if we haven't, then we're going to cover it in future videos. Sound good, John?
Oh, yeah. Let's roll.
All right. All right. So this basically talks about all the types of chromatography and separation. And what I wanted to do with this slide is basically just to show you how many types there are. That's why this topic is so confusing. Okay, you got liquid extraction, distillation, column chromatography. That includes ion exchange, affinity, size exclusion, gas chromatography, TLC, high pressure liquid chromatography. You do not have to be a master at all of these to get questions right on the MCAT. Okay.
Yeah, and some like people, some practice exams, some third party exam vendors, they will like test some of those really, really hyper specifically. Like I know that Altius, they're my favorite third party exams, but they test high pressure liquid chromatography like it is their dying mission. And it's
And let me
just
tell you,
not.
I have never heard of that. I have never heard of that before the MCAT.
Yeah, no, me either. I've never heard of it since the MCAT. But the AAMC and what I've seen on test day is like ion exchange, size exclusion, and I think I've seen TLC.
I've seen TLC and I've seen because I remember it has like to do with retention factor. I think I've
Mm-hmm.
done some
Yeah,
questions
yeah.
about that. I may have seen a gas chromatography. I may have, but that might have been because Altius, that's another one that they kind of, I feel like,
Yeah, they hit gas a lot.
talk
And
about a little
maybe
more.
distillation on the AAMC. Maybe I've seen a distillation one,
Maybe.
fractional,
Yeah,
but
maybe. Let me tell you what
probably
you're
not.
not going to see. You're not going to see affinity chromatography. You're not going to see probably vacuum distillation, just those obscure ones. You're not going to see liquid extraction. And if you are, you're really actually being tested on solubility. You're not being tested on liquid extraction.
Low key, when you said liquid extraction in the intro, I was like, ugh, that's a retake. She misspoke. Like I didn't know it was a thing.
Yeah, I was stuttering.
Yeah. I was like,
Yeah,
this
no.
idiot. How is she related
I
to
loved
me?
I loved it. I love doing them because I like inverting the little thing and then you got to worry about the glass blowing up. And so I remember
I don't know what you're talking
specifically,
about.
I almost blew up. Y'all know what I'm talking about. I almost blew up the glass thing in a liquid extraction because I forgot to like release the gas. Moving on. What's the
I know what
point
you're
of
talking about
chromatography?
now.
Thank you.
I thought
Okay,
that was
yeah,
part of
you got
fractional distillation, but I know what you're talking about now. Yeah, you separate like the organic layer from the um
inorganic layer.
inorganic layer.
I got you. Shotty.
There we go.
Okay. You want to talk about
Yeah,
kind
let
of
me
the
talk about
point of
chromatography and
chromatography?
separation. So, whenever we're talking about chromatography, um, It says molecules are often in solution with other molecules following chemical reactions. We can separate these molecules based on some physical characteristics that differ between the molecules in solution. So what this is saying is that in chromatography as a whole, we're just taking advantage of the fact that basically molecules that have similar physical capabilities and similar physical capacities are going to stick together. And so we can separate them based off of that.
Yeah. And I will say occasionally you'll see a wrench thrown into that, like how acids dissolve in basic solutions. And so you might see some of that play into it. But typically, like we're dealing with polarity or something like that, or boiling point or charge, where same sticks with same, you know.
Yeah,
And
and
I
you
almost
really
put on here,
go ahead.
I was just gonna say, I almost put on here, like I actually had it written out, like polarity would be like thin layer chromatography, and boiling point would be gas chromatography, but it got real wordy. So we're only really gonna point like to what you're separating, or what you're basing your separation on for the specific chromatography techniques that we're going to talk about. So don't worry about that.
You should, though. You should have a flashcard that knows, like what does TLC use? You should know how that separates things, because they're going to ask you to calculate an RF value, which is essentially how far your solvent's going to climb that piece of paper. And you need to know, based off of polarity, which one would run further.
Yeah,
We're just not going to dive too deep into it. Words.
agree. And speak of the devil,
Oof.
thin layer chromatography, the first one up. And that's probably because it's the most simple and it's widely applicable. And that high pressure liquid chromatography that we were talking about earlier, the reason I don't give a crap about it is because it has the exact same rules as thin layer chromatography. And so I always just kind of like thought about TLC in that, when I was presented with high pressure. It separates based on polarity. In the typical TLC setup, which I kind of have in a picture at the bottom, the mobile phase, okay, when we talk about chromatography, we always have a mobile phase and a stationary phase. The mobile phase is typically a solution that moves, and the stationary phase is typically, in TLC, it's a silica sheet, like a sheet of silica that you literally sit in the mobile phase. The mobile phase is typically non-polar. A lot of times it's something like hexane, some kind of solution like that. Whereas the stationary phase, like I said, is going to be that silica paper. If you're not familiar with it, basically you dot things, you dot different solutions. So probably these would all be known solutions, and this will be like an unknown solution. And you dot them, and you see how the different components that are in that unknown solution separate based on polarity. So you can see this is like a brown dot at the bottom, but once it separates out, part of that brown dot, like it has obviously 4 different chemicals in it. Okay. And one of the chemicals is pretty polar. So it doesn't move up with that hexane. Then as you go up, they get more non-polar. John, I know I'm explaining that crappy. Help me out.
No, you did a good job. The I remember doing this in lab at Ole Miss, and what we did is we took like um like some NSAIDs, some common painkiller, or yeah, some common like over the counter NSAIDs and stuff like that, anti-inflammatories, and then we had one vial that was a mix of all of them. And so let's just say purple was Tylenol and green was ibuprofen and red was aspirin. Gray at the bottom, right above 3, would have been a mixture of all of them. And so it would actually separate out into the 3. So it would stain specific dots at each of the 3, and that would be the specific components of that mixture. So it's a really, really cheap way. That's one reason it's so popular in the chemical field, but it's super easy to do thin layer chromatography. But I think you did it well.
Yeah.
I mean, you've just got to there's some basic chromatography principles, like mobile phase moves, stationary phase doesn't move. It's funny how that works. And the thing that's unique to TLC though is retention factor. And so you do need to associate retention factor with TLC, because that is not, to my knowledge, that's not associated with any other form of chromatography.
I don't think so. There's retention time in gas chromatography, but that's
Mm-hmm.
not the same thing. And to okay, so I got some terms here that are common terms when you're talking about the certain types of chromatography. So thin layer chromatography, like John just said, retention factor is a huge term that's thrown around. Also solvent front, and these two go hand in hand. What the solvent front is where the solution ends up. So I've set my silica plate into my hexane. Originally, it's only like up to this line right here, or maybe even a little bit below it. John, can you see that color?
Yeah. It being the mobile phase, the liquid, by the way.
Yeah. So it would be like right here. I'll make it red. And then through capillary action, it would move up that paper. That's kind of the whole point behind TLC. So it only moves up to a certain point, though, and that point is right here in the picture, and it's called the solvent front. So to calculate your retention factor, you take, oh gosh, I've gotten myself into some deep water trying to pull out of my memory the equation for retention factor.
I'm so glad you didn't ask me to do it. Now you get to look like the stupid one.
I'm pretty sure it's the length of, let's take this purple dot right here. It's like the length from the center of the dot down to like the spotting line, divided by the entire length of from the dotting line to the solvent front. That might be backwards. Y'all fact check me, but I'm almost positive that's it.
I think that's right, because
I
you would
have a
not
note
expect
here.
one greater than 1.
That's exactly
You
right.
wouldn't
So I
expect a
explained it right.
retention
You don't
factor
have to
greater
fact
than
check me.
1.
I am the fact checker.
I thought about capillary action
So
this week, and I went to the fair, and because I hate my gallbladder, and I had some cotton candy, and I threw it at like a little puddle of. I thought it was water then, but now reflecting on where I was, it probably wasn't water. But
vomit.
it was like carny juice or something, heroin. But yeah, so like just a little bit of the cotton candy was touching the water, and it just kind of sucked it all up.
Yeah.
Capillary action. You'll
I
never forget it.
I got a quick story about a carny, John. One time I was at a carnival in Pontotoc, Mississippi, where I'm from, and that's first off, don't get on any rides at a carnival in Pontotoc, Mississippi, because
No,
they're
they're
all
all
shaking.
attached. They are all attached to a pickup truck, very visibly.
Yeah, exactly. Like as you ride it. But there was a carny, and he was not smoking a cigarette, but he opened his mouth to speak at me, and smoke came out. He was not holding a cigarette. He had not. I'd been watching him. He had not just come back from a smoke break. I was like, he's a dragon, or oh my gosh, he's literally like expelling smoke. Like his blood is more smoke than it is CO2.
You just got to start a slow
Anyway,
clap at that point.
I know. I was like, oh my God. Anyway, um, I have a note here that thin layer chromatography is not used for separating entire solutions. We talked about liquid extraction. If you remember anything about that, that is used for separating entire solutions. This is not. This is for identifying how many molecules are in your solution by separating a very small sample, just like John was talking about those NSAIDs. And I want to mention something real quick too here, because it's applicable to every type of chromatography. TLC can be reverse phase. That just means that in that case, the mobile phase will be polar, and the stationary phase will be nonpolar.
But what will the MCAT passage say in that case, Maggie?
It'll say it'll be reverse phase. A lot of times it'll say the mobile phase is polar and the stationary phase is nonpolar.
Yeah, at the very least, it will literally say reverse phase. So don't
Yeah.
worry that like you're just gonna like they're not gonna give you like some kind of obscure thing and expect you to know what the phases are. This is the
Yeah.
classic
Or like
phase.
some,
Go ahead.
yeah, this is traditional. Oh my gosh.
Erase it.
This is
That's
traditional.
traditional, and then if they say reverse phase, just flip it, and that's true for all these chromatographies.
Yeah. All right. I give an honorable mention to gas chromatography just because we do like Altius here and they do have it a lot on their practice exam. So if you want to pause and read this, because I went ahead and used my 5 minutes of my life to make this slide. So if you want to pause it and read it, that's fine, but we're not going to go over it. Ion exchange. Ion exchange chromatography does not separate things based on polarity. It separates things based on charged. So what is the mobile phase? It's charged liquid. Okay, we're going to get into it. And then the stationary phase is charged polymers. So let's
Polymers would
do
be
a
like
little
just little
demonstration here.
beads, by the way.
Yeah.
Maggie and I,
I
whenever
don't
we were
know.
prepping this session, we were talking, and chromatography as a whole is just so like convoluted because there's so many like fancy sciencey terms and stuff like that. But it's really easy when you boil it down. I mean, like TLC, you're just sticking a piece of paper in some liquid, and if it's similar in polarity to the liquid, it's going to rise really high, and if it's not going to rise that high. Ion exchange, you got some beads that are charged, and if your liquid is the opposite charge of those beads, it's going to stick. I mean, you really do need to try to like simplify this stuff to where you could teach it to someone that didn't quite understand the terms that you're using.
Yeah, exactly. And that's why chromatography is so hard. Like even the word chromatography is too many syllables. But like if you kind of, you know, simplify it down into layman's terms, I've drawn over here on the left hand side of the screen um kind of what it looks like. I mean, it's literally like a column just like this, but I just kind of redrew it up here so that we can see the charge of the polymers. Imagine they're literal beads in there, okay? And you pour your solution through these beads. And just as John said, if it's negative, obviously it's going to stick to those positive beads. So what's going to run through, if you have, let me zoom in on my picture here. This is my sample mixture. It's got a bunch of different stuff in it. Okay. Negative, positive, neutral. It's got a bunch of different stuff, but we're trying to get the negative stuff. Okay. We're anion exchange, if you could say. So as it goes through these beads, it's going to separate itself based on charge. So the positive stuff is going to be like, oh, don't touch me, polymers, and go straight through. Okay. So this first elutant is what it's called. When it elutes out, it comes out of the spigot or whatever.
I
That's
did
going to
like
be
that
your
word.
positive charge. Yeah, it's a nice one. I thought about it right just now. And then you're going to have sort of the neutral stuff that's going to be like, I don't really care about these beads. I'm bumping into them, but whatever. I'm not going to avoid them like the positive. I'm just going to kind of come out and I'm going to be neutral. Okay, that's like this purple right here. But the negative stuff is going to hold on to those beads. It's going to stick to them. And so it's going to stay there for literally like a longer amount of time. And eventually, you're going to have to wash it out with a salt solution to basically have something that likes that positive charge even more than your negative charge that you're selecting for. So, probably like an even more um, negative like molecule
More
that would
electronegative
come in.
molecule. That's why you use
Yeah, more
salts, right? They're just
electronegative.
straight up electrolytes, and so they're going to bind that bead a lot tighter.
Yeah, they're basically going to be like, get out of here. This is my polymer. And so finally, your negative solution is going to be washed out. And that's what you're going to be left with at the end.
Righty.
All right, I used a word here. I used elutant. That's a term that's common in all the column chromatographies. Column chromatographies are chromatographies that happen in a column that looks like this. So that would be ion exchange, affinity, size exclusion. It's just kind of an overall catch-all term, but ion exchange specifically. What else?
So the ion exchange chromatography can be broken down into two separate categories. And the categories just describe the charge that you are selecting for. Okay, not the charge of the polymers, but the charge you were selecting for. Cation exchange and anion exchange chromatography. And that's the way it'll be written on the MCAT. You'll see an anion column. They won't say an ion exchange column that uses negative beads. No, they will say a cation exchange column. And so look out for those. You know, that's definitely something you need to make a note of. And I don't think it would be tested, but the way that you will like elute out progressively more, I guess in our case, positive ions is that you're progressively you're washing them in between each vial that gets taken with a salt solution. It's just getting progressively saltier. And so the concentration of salt will increase as you do continuous washes.
Yeah, so that's why you see all these vials in the middle that are basically just like, I mean, like literal like salt water, or maybe like a salty non-polar solution that wouldn't affect anything else. But yeah, just like John said, they get washed through every time to make sure that you're selecting for a single molecule and not just like some that kind of got stuck and don't actually belong in the fully negative charge solution. All right. John, anything else? I don't think so. Oh, this one is used for separating entire solutions, unlike TLC, which was used for just identifying separate solutions in a dirty sample or whatever you want to call it. This is used for separating entire solutions. This is like my favorite chromatography.
You can explain it then.
Okay. It separates molecules based on size, and this is used for, again, separating entire solutions. So you got a solution, and it's got a bunch of different sized molecules in it. So you want to separate based on size. Your mobile phase is going to be the solution at large. So you're just like dumping your solution into this size exclusion chromatograph. And then your stationary phase are porous inert beads. Inert means it doesn't react with anything. And porous means, you know, if this is the bead, like it kind of blew up the bead here, it's got these like canals in it. Okay. And the canals are different sizes. You can see this one over here on the right is pretty thick. Okay. But this one right here is smaller, it's thinner. And that's what they look like in the size exclusion chromatography. So you can imagine if you're pouring in this that has a bunch of different size molecules in it, just like this picture shows. I love this picture. Those big molecules cannot get in those little crevices, and so they completely like bounce around the porous beads, and they actually elute first. Whereas the medium-sized beads, they can go through some of these tunnels, but they can't go through those smaller ones, and so they kind of have to take some time to go through those porous beads. They elute second. Those small molecules, they take their dang time. They have to go through what's called they have to go through a very complicated route is typically the way that it's said. They have to go, and the beads will probably be even more porous than this. They'll have stuff going everywhere, but those small molecules will have to go through all those little tunnels just because they are small enough to fit through it. So gravity's going to pull them through. and they will elute last. There's no like reverse phase for this. This is the way that size-exclusion chromatography always runs. Your big molecules elute first, your smallest molecules elute last.
You do like it. Yeah, you explained
I
it
do
well.
like it. I really like it. Thanks.
You look like you're sweating.
It made no sense to me. That's because my AC's out, John.
Let's get to some questions.
Yeah, literally. Also, it's called gel filtration chromatography occasionally, but not that common. All right, John, me or you? Me or
Go
her?
for it.
Okay. It says researchers use reverse phase high performance liquid chromatography. You see what I'm saying? Polar mobile phase and non-polar stationary phase, okay, to separate compound 2 from compound 1, which statement accurately describes this process. Okay, so a couple things. We got reverse phase. So it tells me that my mobile phase is polar and my stationary phase is non-polar. To separate compound 2 from compound 1. Those were given to me in the passage. Here we go. That's better. Those were given to me in the passage, so I put them right here. You didn't need to know anything else about the passage. You just need to know these two molecules right here. So what are some things I note? I know that high performance liquid chromatography is a really great analog with TLC or thin layer chromatography. So I'm looking at polarity. Okay. So I want to look at basically what's the difference in the polarity between these two. Before I go even into the answer choices, I noticed that compound 2, the only difference is that it has this alcohol group right here. That's the only group. And so that makes it more polar than compound 1. Okay. So I'm more polar in compound 2. That means compound 2 is going to stick with the mobile phase more. I hope that makes sense to everyone because the mobile phase is the polar one. And compound 1 is going to stick more so, slightly more so, because it's just one alcohol group difference, right? But it's going to stick more so with the non-polar stationary phase. Oops. Okay. So the answer choices say A, increasing the polarity of the mobile phase will decrease the retention time of compound 1 relative to compound 2. All right, well, if I'm increasing the polarity of the mobile phase, I'm not fully convinced that I'm just going to decrease the retention time of compound 1. And I say just compound 1 because it is relative to compound 2. So I don't think it's going to I think it's going to have the same effect on compound 1 and compound 2. Compound 2 is still going to stick a little more with the mobile, and compound 1 is still going to stick a little more with the stationary. So I don't know. I'm going to say maybe on that one. Whoops. B says compound 1 will elute first because it is more polar than compound 2. No, it's not. Right? C, decreasing the affinity of compound 1 for the stationary phase will increase its retention time relative to compound 2. No, because retention time would be how long it stays in the stationary phase. And so if you decrease the affinity of compound 1 for the stationary phase, it's not going to stick with the stationary phase for a longer amount of time. So I don't really like that one. D says compound 2 will elute first because it does not interact as favorably with the stationary phase as compound 1. Yeah, absolutely. That basically just means that compound 2 is more polar than compound 1, which was our first thing that we realized. Yep.
The hard part about that question is just keeping everything straight.
Mm-hmm.
Read it very carefully. as Maggie did.
Me?
No, not
Oh,
you.
oh,
No, no, no.
I was like, I thought I read it pretty carefully.
No, 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 not you. You
Um,
did well. I'm just trying to give advice.
yeah, yeah, yeah. Okay. Me or her? John?
I guess I'll try it. I'm a little nervous.
You
The
should be.
relationship between the steroid hormone estrogen and the peptide hormone insulin is being investigated. In order to quantify levels of each of these hormones, tissue samples were homogenized and then placed in a mixture of 2-to-1 hexane to water. So hexane is more nonpolar. So I'll hit you with this MP. And then water is
Girl,
more
I got you
polar.
with the writing. Don't even try with that annotate.
I feel like I'm pretty good with it. This is way better than my actual handwriting.
Actually, it's
It is. What is expected? What is the expected result from this extraction method? Okay. Let's see. So, I'm sorry, Siri is talking to me. Okay, so A says estrogen would be in the hexane phase, insulin would be in the aqueous phase. Okay, I see what they're saying now. So, estrogen is a steroid hormone, which means that it's going to be more nonpolar. In P, who we be? And insulin is a peptide hormone. And a characteristic of peptide hormones is that they are aqueous, meaning that they're going to be more polar in nature. Okay, so A says estrogen would be in the hexane phase, insulin would be in the aqueous phase. I don't hate that. I'll say maybe A. B says both estrogen and insulin would be in the aqueous phase. No, I don't like it. I do hate that because steroid hormone or estrogen is a steroid hormone, which means it's made out of lipids, which means it's not aqueous. So say maybe not to B. C says insulin would be in the hexane phase. I dislike that already, and I feel like I am catching on to a trend here. D says, yeah, let's hurt its feelings. I like that. D says both estrogen and insulin would be in the hexane phase. That one's stupid too. How can we hurt its feelings?
I got an idea.
I got it.
Let's make it so irrelevant that it's not even on a PowerPoint.
It's not even an answer choice. So don't like that either. So basically all this was saying is, hey, you need to pick up on the fact that steroid hormone means nonpolar, peptide hormone means polar, and just decide which of these would belong in which phase. So I would go with answer choice A.
And A is correct. You described that very well, John.
Thanks. I was very nervous.
You know how did you guys see how John had to get a little bit of information from the answer choices to be able to simplify this question and really understand what it's asking? That's okay. Like I feel like more than 50% of my questions, I have to peek at the answers to even see what it's trying to ask me. But still, simplifying the question stem is always going to help. All right, I'll take this. A protein with which properties will most likely have the largest negative net charge at pH 7. Okay, we got a protein, and we're looking for a large negative net charge. Let's see. A says a protein that binds to an anion exchange column at pH 7. So anion exchange, that means we're selecting for anions. And we have positive charged beads. A protein that binds to an anion exchange column at pH 7 and requires a high concentration of NaCl for elution. So that means it's going to be sticking to those beads pretty good. So I like that answer. A says a protein that binds to an anion exchange column at pH 7 and requires a moderate concentration of NaCl for elution. Okay, so it's basically the same thing as A, except not as strong of a negative charge. So I don't like that. I'm looking for the largest net negative charge.
So
A
how did you
protein
get
that binds to a
not as
cation.
strong of a negative charge?
So if it only requires like a moderate concentration of NaCl for elution relative to a high concentration, that means that it's not going to take that much negative charge to push it out because it's not a very negatively charged protein to start with.
Okay, I love it.
Okay. A protein that binds to a cation exchange cation exchange selects for cations. So that would be selecting for a positive charge. Girl, what does that say? Oh, stupid. I thought you were writing selects for cations. I was like, it ain't even close. D, a protein that binds to a cation. A.
I didn't know that I could do this on your screen share. We're just learning
Really?
things.
Okay, well, these sessions are never going to be the same now that you found that out.
No. They will
Okay,
never be
guys.
productive either.
And no one will ever be able to read anything. All right, that's the end of the question, guys. Thank you so much for logging on with us and talking about chromatography, which is kind of a really boring topic in chemistry, but we hope that we made it fun and easy and manageable. We can't help you with the percent yield, though.
Oh, no. Nobody expects that. But make sure to subscribe to the YouTube channel and hit the like button. It helps support us in the best way that we prefer. So thanks for tuning in, and we'll see you next week.